Ever wonder how your phone just knows it's you? Or how a self-driving car can spot a pedestrian from a block away? It seriously feels like magic, right? But it's not. It's actually the result of this one revolutionary idea that taught computers how to see. So let's unpack the genius behind what we call convolutional neural networks. It really all starts with what seems like a simple question. How do we teach a machine to look at this grid of colored dots, pixels, and know, without a doubt, that it's a cat? For the longest time, this was a massive, massive hurdle for AI. So, to really get why this was such a breakthrough, we have to go back and understand the problem. For decades, the way we tried to do machine learning just could not get a grip on images. Let's dig into why. The old method used a standard neural network, sometimes called a multi-layer perceptron, or MLP. And the approach was, well, kind of brute force. It would take a perfectly good 2D image and basically run it through a shredder, flattening it into one super long single line of pixel values. And right there, that's the fatal flaw. That flattening process completely obliterates the most important information in the picture. A pixel that was right next to another one forming the edge of a cat's ear, now it's just lost somewhere in a gigantic list. The network loses all sense of space, which is literally how we see shapes and objects. And if that wasn't bad enough, this method was a complete computational nightmare. To process just a kind of small 1 megapixel image, a single layer in the network would need about 1 billion parameters to tune. 1 billion! That wasn't just impractical, it was totally impossible back then. Clearly, we needed a whole new way for AI to see. And that better way? It came from this really powerful idea, inspired by both biology and math. This was the convolutional breakthrough, and it changed computer vision forever. Okay, so the heart of this new approach is an operation called a convolution. Instead of trying to look at the entire image all at once, the network uses this small sliding window, we call it a kernel, to scan across the image. You can think of this kernel as a tiny detective, looking for one very specific clue, like a vertical edge, a sharp curve, or maybe a fuzzy texture. And this is all built on a really simple but kind of profound principle: locality. The network just assumes that to understand one tiny part of an image, you only need to look at the pixels immediately around it. It works on small, local, manageable chunks, and by doing that, it respects that spatial structure that the old method threw away. The second huge idea is something called translation invariance. And honestly, this quote just nails it. It doesn't matter if you find Waldo in the top left or the bottom right of the page, he's still Waldo. A CNN learns to spot a feature, say the pointy shape of a cat's ear, and once it knows what that looks like, it can find that same ear anywhere else in the picture. So how does this little detector actually work? Well, the math is surprisingly simple. The kernel just slides over a patch of pixels, multiplies the numbers that line up, and then adds it all together into a single number. If that number is high, it's like the kernel is shouting, "Hey, I found the feature." If it's low, it's a "Nope, nothing here." That's it. That's the core operation that powers this whole thing. Okay, so convolution is the heart of the engine, for sure. But it doesn't work alone. You need a few other clever pieces to assemble the whole vision system and make it truly powerful. Think about it. One kernel can find one type of feature, like a vertical line. But what if we want to look for hundreds of different features all at once? That's where channels come in. It's just like how a photo has red, green, and blue color channels. A CNN has many channels, so it can search for vertical lines, horizontal lines, green patches, and fuzzy textures all at the exact same time. Now, there's a small problem you run into when you stack these layers. Every time you do a convolution, the image gets a little bit smaller at the edges. To stop it from just shrinking away to nothing, we use a simple trick called padding. We just add a border of extra pixels around the outside. It's a simple fix that keeps everything running smoothly. To keep things running fast, we don't always have to slide our little detector 1 pixel at a time. That can be slow. So instead, we can tell it to jump or stride across the image. Using a larger stride makes the whole process faster and shrinks the output, which means less work for the next layer. All right, and finally, after the network has found all these different features, it needs a way to kind of zoom out and summarize the results. This is called pooling. It shrinks everything down by taking the most important information from a small neighborhood of pixels. This not only makes the network way more efficient, but it also helps it recognize an object even if it's shifted around a little bit. There are 2 main ways to do this. The most popular one is max pooling. It just looks at a window of pixels and picks the biggest number. It's basically asking, what's the most prominent feature I see right here?
Then there's average pooling, which, well, it takes the average. It gives you a more blurred general summary of the area.
So we have all of our building blocks now. Convolutions, channels, pooling. Let's see how they all came together in one of the first truly successful CNNs, a real pioneer in the field.
You know, these ideas didn't just appear overnight. They were being developed for years. But in 1998, a researcher named Jan LeCun and his team introduced a network that would become an absolute landmark, LeNet 5.
And here's the really cool part. This wasn't just some theory in a research paper. LeNet 5 was so good at recognizing handwritten numbers that it was actually deployed in the real world to read the digits on checks that people were depositing at ATMs. For real.
And the way it was built is just so elegant because it tells a story. It starts with convolution and pulling to find simple features, basic lines and curves. Then it does it again, combining those simple features into more complex ones, like the loop of a 6 or the corner of a 4. It's only at the very end, after all that smart feature detection is done, that it flattens everything to make a final decision. It's a beautiful example of all these pieces working together. So that really brings us to a final thought. LeNet proved that this was the right path. It laid the foundation for everything we have today in computer vision. And it just makes you wonder, if a network from the 1990s could reliably read our messy handwriting, what are the real limits for the enormous, incredibly sophisticated networks we can build today? What can they truly learn to see?